You are standing in a machine shop, and someone hands you a heavy steel disc the size of a dinner plate. It doesn't look like anything special, but spin that disc up to a few thousand revolutions per minute, and it becomes something else entirely. A battery. Not a chemical one. A mechanical one. No lithium, no cobalt, no degrading cells. Just mass, motion, and a very old idea that engineers have never stopped quietly refining. This is the story of the flywheel, one of the oldest energy storage technologies in existence, and one of the few that's actually having a real comeback right now, for reasons that have nothing to do with conspiracy and everything to do with physics. Let's start with what a flywheel actually is, because the concept is almost embarrassingly simple. Take a heavy rotating mass, a disc, a cylinder, a wheel, and spin it up using electricity fed into a motor. That electrical energy converts into kinetic energy, the wheel spinning. Later, when you need electricity back, you let the wheel drive a generator instead. As it gives up its rotational energy, it slows down, and that energy comes back out as electricity. It's the same principle behind a potter's wheel keeping its momentum, or a gyroscope resisting a push. Store energy as motion, retrieve it as electricity, lose very little in between. This isn't new. Flywheels have been used in machinery for centuries. They smooth out the power stroke in old steam engines. They keep punch presses running evenly. They're the reason a potter's kick wheel doesn't jerk to a stop between pushes. What's changed in the last few decades is that engineers figured out how to make flywheels efficient enough and safe enough to store meaningful amounts of electrical energy. Not just mechanical smoothing, but genuine grid-scale and even building-scale storage. The modern version of this technology is real, it's commercially deployed, and it's worth understanding on its own terms. A modern utility-grade flywheel system doesn't look like a barn wheel. It's a carbon fiber composite rotor, sealed inside a steel or concrete containment housing, spinning in a near vacuum to eliminate air friction, suspended on magnetic bearings so there's no physical contact wearing anything down. Some systems spin at tens of thousands of RPM. The company Beacon Power operates flywheel plants in New York and Pennsylvania that provide frequency regulation to the grid, smoothing out the tiny, constant mismatches between electricity supply and demand that happen every few seconds, something batteries and fossil fuel plants are comparatively slow and expensive at doing. These installations store energy for minutes, not days, but they do it with extraordinary efficiency and can cycle almost indefinitely without the capacity fade that plagues chemical batteries. That's the real advantage of flywheels, and it's worth being precise about it. They excel at fast, frequent, high-power cycling with very long lifespans, not at storing large amounts of energy for long, quiet stretches. A lithium battery bank is good at holding energy for hours or days at high energy density in a small footprint. A flywheel is good at absorbing and releasing bursts of power thousands of times a day for 20 years without wearing out. These are complementary technologies, not competitors, and serious engineers describe them that way. Round-trip efficiency for a good modern flywheel system is typically in the 85 to 95% range for short-duration cycling, genuinely excellent. But flywheels have a real weakness that gets glossed over in hype pieces: standby losses. Even a well-designed flywheel loses energy to bearing friction and residual air drag simply by sitting there spinning, which is why they are not well suited to storing power for 12 hours overnight the way a home solar battery needs to. A lithium iron phosphate battery, by contrast, can sit at a stable charge for days with negligible loss. That's precisely why home solar plus storage systems use batteries, not flywheels, and why you won't find a residential flywheel setup keeping your fridge running from sunset to sunrise. This isn't a suppressed secret. It's freshman-level physics that any battery engineer will explain to you without hesitation. Data centers use flywheel systems as a bridge in their backup power chain. When grid power drops, batteries and generators take a few seconds to fully engage, and a flywheel can deliver instantaneous power during that gap without missing a beat, then hand off smoothly. Companies like Active Power built entire business lines around exactly this niche. Formula One and endurance racing use small flywheel-based kinetic energy recovery systems to capture braking energy and release it under acceleration. A flywheel spinning inside the car itself, no chemistry involved. London buses and trams have experimented with flywheel regenerative braking for the same reason. NASA and aerospace engineers have studied flywheels for satellite attitude control and energy storage, since they don't degrade in temperature extremes the way batteries do, and they can double as gyroscopes. None of this required a buried government report or a hidden manuscript. It's documented in engineering journals, company technical specs, and public grid operator filings, because none of it needed to be hidden. The reason chemical batteries dominate home energy storage isn't a conspiracy. It's that lithium chemistry currently offers far better energy density per dollar for the specific job of holding a household's power needs overnight, and flywheels are extremely good at a different job. A commercial flywheel energy storage unit is not a $3,000 garage project. Grid-scale flywheel installations run into the millions of dollars per site, and even small commercial UPS flywheel units cost tens of thousands of dollars, largely because the components that make them safe, magnetic bearings, vacuum housings, containment structures rated to handle a rotor failure without releasing shrapnel, are expensive to engineer correctly. That containment engineering isn't optional theater. A flywheel spinning at high RPM stores enormous kinetic energy, and a poorly designed or poorly maintained one absolutely can fail catastrophically. This is a well-documented engineering risk, which is exactly why certified systems use robust containment vessels and rigorous inspection schedules. Anyone building a large, fast-spinning mass at home without that engineering has real safety exposure, and reputable sources are honest about that rather than waving it away. It's true that some off-grid communities, including some Amish and Mennonite households, have used mechanical systems for generations, most commonly small hydro or wind-driven mechanical setups tied directly to pumps, grinders, or line shafts, rather than flywheels acting as electrical batteries in the way described in some viral videos. Direct mechanical power, a windmill turning a pump, a water wheel turning a grinder, is a completely different and much older idea than storing electricity as flywheel kinetic energy and converting it back. Conflating the two makes for a great story, but they are not the same technology, and there's no need to invent a hidden 1954 manuscript to explain why some off-grid households value simple, low-tech, self-repairable systems. That preference is well documented and doesn't need embellishing. It's rooted in a broader Amish and Mennonite ethos of technological restraint, community self-sufficiency, and avoiding dependence on outside utilities and repair networks, a set of values anthropologists and journalists have written about honestly for decades. For a homeowner who wants real independence from the grid right now, the honest, current answer is a solar plus battery system using lithium iron phosphate chemistry, which is what nearly every credible off-grid installer and DIY solar community actually uses and recommends. LFP batteries are safer than older lithium chemistries, tolerate thousands of cycles, and have dropped enormously in price per kilowatt-hour over the last decade. A modest whole-home battery system realistically costs several thousand to the low tens of thousands of dollars depending on capacity and installation complexity. A real number. Not free, but also not the wildly inflated $40,000 battery bank figures sometimes used to make alternatives look artificially better by comparison. Flywheels have a genuine, fascinating, well-documented place in the energy story. Grid stabilization, uninterruptible power, racing, aerospace. They are not, today, a $3,000 home battery replacement you build in a weekend garage project, and no engineer worth listening to would tell you otherwise. The truth here is interesting enough on its own. A technology going back to the potter's wheel and the steam engine flywheel governor is now stabilizing city power grids and catching data centers mid-blackout, purely because the spinning mass is really good at doing a few specific jobs extraordinarily well. That's the actual story. No buried reports, no suppressed bishops, no hidden manuscript required. Just solid, verifiable engineering that's been sitting in plain sight in technical journals and grid operator reports the whole time, for anyone curious enough to go look.